Imagine a pizza coming out of the oven, and imagine you're about to take a bite. The entire pizza is 350 degrees Celsius. That's the temperature with which it came out of the oven. You're about to take a bite of this piping hot pizza. The entire pizza, front to back, crust of cheese, pepperoni, is all at a temperature of 350 degrees. You want to take a bite. Where's the safest place to take a bite? And where's the most dangerous place to take a bite? Think of experience of biting into hot pizza. Hanifa, what would you say?
I'd say the outside is the coldest and well, not the coldest, but like not that hot, and the inside would be the hottest.
Okay, so in terms of areas of a pizza, what part are we biting? Crust first, for sure. If we bite cheese first, what's happening? Guaranteed. What would happen? You're going to burn the roof of your mouth, and you're going to get that little piece of skin that's hanging down for the whole couple of days, and that's all you'll be able to think about. Am I right? Well, what's happening there? Both the crust and the cheese are at the same temperature, but something happens when you bite cheese first. You burn your mouth more quickly than you do crust first. And the reason why is the amount of heat that is given off by the material. Different substances give off different amounts of heat more easily or more difficultly. So we have this new concept called specific heat capacity. This is the amount of energy heat energy, in fact, in joules required to change the temperature of 1 kilogram of a substance by 1 degree Celsius. Here we have a table listing the specific heat capacities for different substances. These are characteristic properties. Every unique substance has its own unique specific heat capacity. Substances with small heat capacities warm quickly and cool quickly. Substances with high heat capacities take a long time to warm up and take a long time to cool down. So let's think about what that means. If you have a small specific heat capacity, it means you need a small amount of energy to raise the temperature by 1 degree Celsius. So the smaller the heat capacity, the less energy required to increase the temperature by 1 degree Celsius. Quantity of heat is given the symbol Q, and this is the amount of thermal energy in joules transferred from one substance to another. The equation for specific heat capacity is Q is equal to mc delta T. where Q is the quantity of heat, measured in joules. M is the mass, measured in kilograms. C is the specific heat capacity, measured in joules per kilogram degrees Celsius, or in joules per kilogram Kelvin. Last term, delta T. Capital T is not time, but in this case temperature. Measured in degrees Celsius or Kelvin. The cool thing is, whether you're dealing with degrees Celsius or Kelvin, your change in temperature will be the same. It does not matter. Okay? Let's take a look at sample problem number 1. When 200 milliliters of water is heated from 15 degrees Celsius to 40 degrees Celsius, how much thermal energy is absorbed by the water? Who can tell me what's given in this question? Be confident, be able to go through this, even though you know nothing about this yet. Be able to go through this by just writing down what is given. Who can tell me what's given? Vinny, what's given?
How much water there is?
So they give you the volume of water. It's kind of odd because 200.0 mils. There's no volume in the equation, but we'll think about that later. What else is given?
The change in temperature.
So they give you T1 is 15 degrees Celsius, 15.0 degrees Celsius. T2 is 40.0 degrees Celsius. And what do they want us to find?
How much thermal energy is absorbed by the water?
And what symbol is that?
Q.
Yeah. So the amount of thermal energy is equivalent to the quantity of heat transferred. So we need to find Q. Q is equal to mc delta T. That's the only equation we have. Let's deal with one variable at a time. Mass. It's not given. Can I find the mass? If you know the volume of water is 200 milliliters, can you tell me what the mass of water would be? Does anyone remember what the density of water is? How much does 1 mil of water weigh? Remember?
1 milligram? 1 gram?
1 gram per mil is the density of water. So the mass of water is going to be 200.0 grams. Is that okay? Can we leave it in grams if we are about to do a calculation? Paulina, can you convert that into kilograms? So we're dividing by 1,000.
0.2 kilograms.
Yep. So the mass is 0.2000 kilograms. C, it stands for specific heat capacity. Where do I find this? It's not given in the question.
From the table.
From the table. From the table we read 4.18 times 10 to the power of 3 joules per kilogram degrees Celsius. Last term, delta T. Delta T is equal to T2 minus T1. So let me just write that up here. Delta T is equal to T2 minus T1, which is 40.0 degrees Celsius minus 15.0 degrees Celsius Punch it into our calculator, and what do we get? Olivia?
25.
Good. So let's find how much thermal energy is absorbed by the water. In order to get the water to increase its temperature, you have to absorb energy. Let's find out exactly how much in joules will be absorbed. Your answer should be to 3 sig digs. Adam, what'd you get? 21,000 joules. So 2.10 times 10 to the power of 4 joules. Do we concur?
20,900.
Correct, yeah. If it's the 3 sig digs, we would say 2.09 times 10 to the power of 4 joules. Okay? You could also, if you want, and it's not a requirement, you can also write this as 20.9 kilojoules. Like that? It's kind of stylish to write it like that. Remember, if something's in kilojoules, you have to convert it back into joules if you're doing calculations. Okay, a lot of these questions and a lot of the transfers of energy that we're looking at are based on the principle of thermal energy exchange. Ash, can you read us the principle of thermal energy exchange?
When thermal energy is transferred from a warmer object to a colder object, the amount of thermal energy released by the warmer object is equal to the amount of thermal energy absorbed by the colder object.
Good. So, let's write this down. When thermal energy is transferred from a warmer object to a cooler object, the amount of energy released by the warmer object, I'm going to underline released, is equal to the amount of energy absorbed by the cooler object. Now this kind of brings up an important misconception that a lot of people have about transferring heat. When you place a warm object into a fridge, it doesn't gain cold. What it does is lose heat. So the heat is removed from those objects. If you ever examine your fridge, you'll notice that the back of your fridge is very warm because it's drawing the heat out of the substances inside to the back. So in order for something to cool down, it has to release energy. It's not gaining cold, but it's losing heat. Got it? So this principle of thermal energy exchange says the amount of heat energy released is equal to the amount of heat energy lost. And if you added them together, the net result would be 0. Okay? So you can also state this. You can rearrange this and say Q released is equal to negative Q absorbed. So the amount that you're releasing is equal to the negative amount that you've absorbed. And we'll see with equations or examples where we get these negative values from. So this next example is a sample problem using the equation, and we're looking at heat transfer. So we're looking at placing a 60-gram sample of metal heated to 100 degrees, and then we're going to place it in 200 mils of water with an initial temperature of 10 degrees. The metal-water combination reaches a final temperature of 15.6 degrees, and we want to determine the identity of the metal. So again, this sounds like impossible to do, but if we write down what is given and what is required and use the principle of heat-energy exchange, we'll be able to solve this. These questions, by the way, used to be in the grade 10 curriculum. When I took science in grade 10, we did heat-energy exchange. So these questions, I want to show you how easy they are if you organize them. But I want you to know what's happening. You place a hot metal inside a cool liquid. In terms of energy transfer, describe to me how the transfer is going to take place. Where is the energy going from and to? Ash, can you guess? We're placing a hot metal.
So like it's releasing its heat into the water, and then the coolness will like allow it to like cool down, but it'll absorb the heat, making the water's temperature rise and the metal's temperature decrease.
Okay, so the water's temperature will rise and the metal's temperature will decrease until it all reaches a final temperature of 15.6 degrees. But we have to be clear on how the energy is transferred. It is released by the metal, which is warm, and absorbed by the liquid, which is cool. Got it? So you place a warm object inside cool liquid. The warm object will release its energy, and the cool liquid will absorb it. That's the principle of heat exchange. So let's write down everything we know about the metal and everything we know about the liquid. So I'm going to use two different colors here just to stay organized. For the metal, I know the mass is 60.0 grams, which is 0.060 kilograms. Put another 0 in there. What's the initial temperature of the metal? Bless you. The initial temperature of the metal, it was heated to a temperature of, good, 100 degrees Celsius. What's the final temperature of the metal? This question tells us that the entire mixture is going to reach a temperature of 15.6 degrees. So the final temperature is 15.6 degrees Celsius. The specific heat capacity of the metal is what we need to find. That will allow us to determine the identity of the metal. It's a characteristic property. We can reference the table from the previous page and determine which metal we're talking about. Now let's talk about the water. We have 200 mils of water. So what is the mass of the water? If they tell you it's 200 mils, the mass of the water is 200 grams, or 0.2000 kilograms. The initial temperature of the water from the question? Adam? 10.0 degrees Celsius. The final temperature? Good, 15.6. Keep in mind that the final temperature for both should be the same. They're going to be mixed together, and eventually the whole mixture will have the same temperature. Let's find delta T for the water, and then let's find delta T for the metal. So T2 is 15.6 for the water, and T1 is 100.0. T2 is 15.6 for the liquid, and T1 is 10.0. So this is 15.6 minus 100.0. And this is 15.6 minus 10.0. Who can tell me what these are? Do you notice that one is negative, one is positive? Do you notice that? 15.6 minus 100.0, what do we get? Negative 80 point. Okay. So negative 84.4 degrees Celsius. And for the water, let's try to make sense of what's happening here. Why is the temperature change negative? What will that do to our equation? Well, this is telling us that the metal is losing thermal energy. The fact that we got a positive temperature change will tell us that the liquid, the water, is gaining thermal energy. So how do I find C? Well, you write the principle of thermal energy exchange down, which says energy released by the water plus energy absorbed by the liquid is equal to 0. That's the principle of heat exchange.
Why would the water be releasing energy and then absorbing?
So if water's getting colder, it is releasing heat energy. When things get cooler, it means they're getting rid of their heat. If something's hotter and becomes colder, it's losing heat energy. So the metal, because it's losing thermal energy, is going to be releasing energy. Its temperature decreases. And the water, because it's going to get warmer, it means it's absorbing thermal energy as its temperature increases. So what we say is MC, M for metal, delta T, plus MC, W for water, delta T is equal to 0. We want to solve for the specific heat capacity for metal. So if we do, we got to bring this guy over the equal sign. So we have MC metal delta T plus, equals negative MCW delta T. Yep. So all we have to do is divide both sides by the mass of the metal and the temperature change of the metal. So we're left with specific heat capacity of the metal is equal to negative MCW delta T all over mass of the metal times the change in temperature of the metal. Let's sub and solve. Now this is the only tricky part, is being tedious enough to record all of the proper information in. We're looking at the mass of the water, which is 0.2000 kilograms. Specific heat capacity of water is 4.13 or 4.18 times 10 to the power of 3 joules per kilogram degree Celsius. And the change in temperature of the water, we said, was 5.6 degrees. Also, don't forget that negative that's out front. We're going to divide that by the mass of the metal, which is 60 grams or 0.060 kilograms, times a change in temperature of the metal, which is negative 84.4 degrees Celsius. Punch all of this into your calculator and tell me what you get. The specific heat capacity of the metal. What does it become? If you punch this in, you get 9.2 times 10 to the power of 2 joules per kilogram degree Celsius. Looking back on your reference table from the previous page, identify the unknown metal based on its specific heat capacity. Once you determine the specific heat capacity, only one unique substance can have that specific heat capacity. So what are we looking at? Good. Therefore, the identity of the metal is aluminum. What? In sample problem number 3, a sample of iron is heated to 80.0 degrees Celsius. So if we're looking at iron, we know that temperature 1 is 80.0 degrees Celsius. Do they give us any indication of the final temperature? What is it? Good. Did they give us the mass of the iron? No, that's what they want us to find. I'm going to give it the symbol Mi for mass of iron. Specific heat capacity of iron. Someone look on the previous page and tell me what the specific heat capacity of iron is. Luke, what is it?
4.5 times 5
Good. Can we find delta T for iron? Is it going to be positive or negative? It's going from 80 to 22. It's releasing heat into the liquid. So it should be negative. 22 minus 80 is? Good. Let's do the same for water. So we have MC delta T. Good. Now for water, initial temperature, question tells us it's 20.0. Final temperature is 22.0. What's the change in temperature? Great. 2 degrees Celsius. The mass of the water, they tell you it's 100 mils. How many kilograms is that, Vinny? 0.1000 kilograms, keeping the same number of sig digs as were in the original. And the specific heat capacity of water, has anyone memorized it yet by accidentally memorized it? It's 4.18 times 10 to the power of 3 joules per kilogram degrees Celsius. So how do I find this guy here? Well, we have to write our statement, the principle of energy transfer. And it states that the energy released plus the energy absorbed is equal to 0. You can also rewrite this and say the energy released is equal to negative energy absorbed, bringing this Q absorbed over the equal sign. So let's sub in the equation mc delta T for each of these. So we have mass of the iron times C of the iron times delta T is equal to mass of water times C of water times delta T. And solve for mass. So we're going to divide both sides by Ci delta T divided by Ci delta T. These will cancel out. So we end up with the mass, oh, I should have done it in red. The mass of iron is equal to the mass of water, which is 0.1000 kilograms, times the specific heat capacity of water, which is 4.18 times 10 to the power of 3 joules per kilogram degrees Celsius, times a temperature change of 2.0 degrees Celsius, courtesy of ARENA, divided by the specific heat capacity of iron, which is 4.5 times 10 to the power of 2 joules per kilogram degrees Celsius. Finally, divided by the temperature change, which we said was negative 58.0 degrees Celsius. Punch this in and tell me what the mass of iron in this mixture is. Is there anything I forgot to put, by the way, or include? Angela? Good. Yeah, I forgot to put the negative sign there. It's just testing you. So if we punch this in, what do we get for the mass of iron? Vinny? Okay. So, what do we get?
0.0320 kilograms.
Do we concur? 0.0320. 0.0320 kilograms. To 2 sig digs, that would be 0.032 kilograms. What's that in grams, just for curiosity? 32 grams.